Good morning. Today, I'd like to continue the path that we've been following. I want to look at the Ricci tensor, the Ricci scalar, and the Einstein tensor. We've already seen that the Riemann tensor has the correct sort of ingredients to be building towards the left-hand side of the field equations, but the Riemann tensor is a 1-3 tensor, and the stress energy tensor is not. If you look at all of the components of the curvature tensor, you can construct a wide variety of other things from it, one of which is obtained by setting the upper index and the middle index on the bottom equal to each other and summing up. These numbers will be the components of a 0-2 tensor, which confusingly we will also call R. This is called the Ricci tensor components. It's not difficult to see, using our locally flat coordinate system, that this Ricci tensor is symmetric. If I form the quantity obtained by taking the components of the Ricci tensor, multiplying by corresponding components of the upstairs version of the metric and adding up, the result is called the Ricci scalar. Some people also call this the trace of the Ricci tensor, because if we were in Cartesian coordinates in ordinary geometry, the G alpha betas would just be the Kronecker delta alpha beta, and the sum would consist of R11 plus R22 plus R33. In ordinary linear algebra, we call that the trace. We have to be a little bit careful because depending on the context and the coordinate system, R is not, generally speaking, the sum of the components of the diagonal entries of the Ricci tensor. Let's go back and look at the Bianchi identities again, which were these kind of formulas. It's worth mentioning that each one of these quantities is the component of a tensor. That tensor has no upstairs indexes and 5 downstairs indexes. So really, mentally, I should think of this 0 as being perhaps a capital Z with 5 indexes downstairs. The components of Z are all 0, though. I'm going to take this identity, I'm going to multiply it by metric tensor components in the upstairs position, and sum over one of the indexes, and sum over two of the indexes. Of course, when you sum up a number of quantities, all of which are 0, you get 0 for an answer. So this 0 isn't the same as the preceding 0. The covariant derivative of the metric tensor is always 0. So in what I'm about to write down, once again, it's going to look like I've made a calculus mistake, but I haven't. Strictly speaking, this covariant derivative component should be G alpha mu times R alpha beta mu nu semicolon lambda plus R alpha beta mu nu times covariant derivative component number lambda of G alpha mu, but that last quantity is 0. So even though I should write out the product rule here, one of the terms is always going to be 0. This quantity and this quantity are always the same thing. Using our raise and lower tensor index idea, though, G alpha mu, R alpha beta mu nu is the same as the mu upstairs, beta mu nu downstairs component of the curvature tensor, then take covariant derivative of that with respect to x number lambda. If you look at the quantity inside the parentheses, though, this is a component of the Ricci tensor. The mu is an index of summation, so what we're really doing here is we're taking the covariant derivative with respect to x number lambda of Ricci tensor component number beta and nu. We will be able to do something that's similar in spirit to the middle term. The third term is going to be a little bit more troublesome, but we'll be able to do something with that as well. The second term, using the same trick as before, can be written in this form. If you'll remember, on each of the first pair of indexes and the second pair of indexes, the lowered version of the Riemann tensor is antisymmetric. So if I interchange indexes lambda and mu, I'll get the negative of, not to be overly picky, but the metric tensor is symmetric in its two indexes. G alpha mu upstairs and G mu alpha upstairs are the same. I want to literally write it in that format because this is the definition inside the parentheses of the negative of one of the components of the Ricci tensor. So the second term in our contraction of the Bianchi identities is simply this number. By doing the same kind of manipulations, we can see that the third term in our contracted Bianchi identity works out to be this. This is slightly less convenient than the other two because the index of summation mu is not one of the lower indexes on the curvature tensor, which means I can't immediately write this in terms of the Ricci tensor components. So taking the Bianchi identities and contracting with the metric tensor in the upstairs index version, we find out that this fact must be true. It relates components of the Ricci tensor in the first two terms, so multiply both sides by g beta nu in the upstairs position, summing over the beta and over the nu. As before, dealing with the first two terms is not difficult, but the third one requires some manipulation. For the third term, we will write out the same sort of expression. I'll bring the g beta nu inside the covariant derivative. To represent the components of the curvature tensor, we will express it in the lowered component version. The motivation for doing that is that the symmetries of the tensor are easier to deal with in the lowered form. For example, if I interchange indexes alpha and beta, what I get is the negative of r beta alpha nu lambda. But because of the way we raise and lower indexes, g beta nu r beta alpha nu lambda is the same thing as r nu alpha nu lambda, and by being very sneaky, the upper index and the middle index on the bottom are the same, so this is an index of summation. R nu alpha nu lambda is the definition of component number alpha lambda of the Ricci tensor. We multiply this by g mu alpha, sum over the alpha, and then do the covariant derivative, summing over mu. Using our raise and lower index properties again, we see that the third term in the double contracted Bianchi identity is just the covariant derivative with respect to x number mu of negative of r mu upstairs lambda downstairs with mu obviously being an index of summation. Combining all of the things that we've figured out, this quantity must be zero, which of course is this quantity, which I'll write in this form, which is obviously equivalent to this form. In the first term, 2r mu lambda semicolon mu, there is a sum having index of summation mu. There is no mu in this second piece. I'd like to rearrange this just a little bit more so that I can have an index of summation. I want to imagine having a sum where there is an index of summation mu here, and yet the only time that I get an interesting term is when mu is equal to lambda. In the second term, the only time you get a non-zero contribution is when mu is equal to lambda, and in that case, the sum works out to be r semicolon lambda. So we will write things this way. However, the covariant derivative of a difference of two quantities, this, is the same as the difference of the covariant derivative of the quantity, that. So I don't feel bad about writing it in this format, finally. Once more, I'm going to contract using the metric tensor. Using the usual trick, I can bring g beta mu inside the covariant derivative, and then one last time we'll use the raising and lowering index behavior of the metric to write this in a form that you may have seen before. This shows that 2r minus scalar r times the metric tensor is divergence free. I do have to make a comment. This would be true if I multiplied the tensor components inside the parentheses by 7 or 12 or any constant. So there is a little bit of wiggle room here. We'll talk about that later. Since we do have that wiggle room in terms of constant factors, I'm going to factor the 2 out. This still has divergence 0. We're going to make up a name for the components inside the parentheses. We're going to call them capital G beta lambda. They are equal to the corresponding component of the Ricci tensor minus half of the Ricci scalar multiplied by the corresponding components of the metric tensor. What we have figured out is the divergence of this is automatically 0. So what do we know? What is the deal with these g beta lambda quantities? They depend on the components of the Ricci tensor. The Ricci tensor is found in terms of the components of the curvature tensor. The curvature tensor is built out of components of the metric, both in the upstairs and downstairs position, the derivatives of such things, and the second derivatives of such things. And we've just found out that the capital G tensor is divergence free. This is the criterion that we said long ago that the left-hand side of the field equations are going to have to satisfy. This capital G is called the Einstein tensor. Our whole motivation for following this line of reasoning was, based on the weak gravitational field situation, we figured out that the field equations ought to look like this. There ought to be some tensor, capital G, which is equal to a constant times the stress energy tensor. This G was supposed to be symmetric, it was supposed to be divergence free, and it was supposed to be constructible from the components of the metric the first partial derivatives and the second partial derivatives of components of the metric. We have found such a tensor, except for one little piece of wiggle room. We now know the field equations. That wiggle room is, what's the constant? Because of what we just said a moment ago, all of these nice properties that we want the left-hand side of the field equations to obey would also be obeyed if we multiplied that left-hand side by 7 or 12 or cube root of pi or something. During our discussion of the weak field case, though, we decided to write the number on the right-hand side in a certain particular way. In the weak field approximation, we figured out that Poisson's equation, Laplacian of the potential, equals 4 pi Newton's constant times mass density, required us to put a factor of 8 pi here. For this to successfully reduce down into the Newtonian situation, in the weak field approximation, this must simplify down into the Laplacian of the 0, 0 component of the metric. That's what we figured out. That would be, in the weak field approximation, 2 times the Laplacian of the potential, and dividing the 2 out would give you Laplacian of potential is 4 pi times Newton's constant times, in the weak field case, the mass density. So I may show this at some later date, but this G-tensor that we have cooked up doesn't need to have any additional factors put onto it. The Einstein field equations, almost, are G mu nu is 8 times pi times Newton's constant times T mu nu. Keep in mind, we're using units where the speed of light is 1. We'll talk more about that later as well. There is one additional piece of wiggle room that we haven't thought about. We have used several times during our discussion the fact that the covariant derivative of the metric tensor is always 0. When we constructed the Einstein tensor, we wanted it to be symmetric. We wanted it to be constructible from metric tensor components and their first and second partial derivatives, and we wanted the divergence of it to be 0. There's one additional thing that we could put into these field equations that acted like that. On either side of the equation, although it's traditional to put it over on the left side, I could add 3 times the metric tensor component, and this wouldn't change any of the nice properties that we want the left-hand side to have. I could add -5 times the metric. I could add 12 times cube root of pi times the metric. We could add a constant times G mu nu to the left-hand side, and then you would still have a tensor that obeys all of your requirements. So we could write these field equations with this new extra idea in as R mu nu minus 1/2 Ricci scalar times the metric tensor. I should comment that that R is a scalar, but it isn't necessarily a constant. It can vary from point to point in the space-time, plus an actual constant times G mu nu equals 8 pi Newton's constant components of the stress energy tensor. This extra constant, capital lambda, is called the cosmological constant. When people speak of the field equations of general relativity, they're speaking of this equation. In terms of unknown parameters, there are only 2 things that you have to match up with experiment. The first is that, which, as we've said, ends up being Newton's constant. And then there's that, which has to be determined by measurement. If we want to make things as obscure looking as possible, we'll write the name of the Einstein tensor plus lambda times the name of the metric, understanding that it's in the upstairs component form, is a constant times the t tensor. This is very compact and hides very effectively the fact that there are hundreds and thousands of individual terms to be looked at when you look at this equation. Einstein himself never believed when he wrote this equation down that anybody would find analytical solutions of it because it was just so complicated. Einstein actually used approximation techniques to get estimates of the consequences of these field equations. He was very surprised, less than a year after this had been published, that someone actually found an analytical solution. We'll talk about that coming up. In the meantime, I hope everybody's having a good day. I'll talk to you again soon.